Michael. Next slide, please. Thanks. So unfortunately, my movie's broken. But for those of you who aren't familiar, I know Amy gave a great introduction, but very quickly I wanted to go over the Neowise mission. This is a sun-synchronous infrared telescope currently in orbit around the Earth. It uses a 40-centimeter telescope and has 4 wavelength bands. 3.4 and 4.6 microns have always been in use, and 12 and 22 microns are 2 bands that were in use when there was cryogen during the main part of the mission. As I said, it's in sun-synchronous orbit around Earth, and it takes an image every 11 seconds, regardless of weather. You know, everything's very beautiful. Weather's always clear in space, and it's always night, so that's great. Next slide, please. So this is the work that I do with the team, and we study thermophysical modeling. This is a very powerful tool for investigating asteroid surfaces. It gives you an average surface thermal inertia of the body, and that'll tell you about how the surface resists temperature change. It's defined as the square root of thermal conductivity, heat capacity, and density. And it can tell us a lot of even though it's a simple measurement, it can tell us a lot of things about the asteroids themselves, such as how much dust is on the surface. And if you see a lot of dust, you might imagine that it's undergone a recent collision. There's obvious cross-applicability with spacecraft design. If you're going to land any sort of spacecraft on these objects, you want to know how much dust there is, how many rocks there are, and those sorts of general things, as well as the temperature gradients. And finally, it tells us how the surface reacts to heat, and that gives us the strength of the Yarkovsky effect. Lance just explained this very well previously, so I'm not going to go into it in depth. But the Yarkovsky effect is a very important force for both determining hazard and if you're going to determine how asteroids get from the main belt to near Earth space. Next slide, please. So this is a schematic of how thermophysical modeling generally works. You start with some sort of shape model and known spin state, and that can either come from light curves or from radar models that Michael just talked about. Whoever designed the schedule did a great job. Thank you. It's really set me up well. And what you do is you take these shape models and you run a code that sees how that calculates how heat transports across the surface, given an assumed thermal inertia. And that'll give you a range of different temperature maps. And from those temperature maps, you can integrate the total infrared flux from that temperature, and then you get a point source that you can match to a Neowise magnitude that's been observed. So again, this is disk integrated for the types of things we do with asteroids, but it can still tell us a lot about the surface properties generally as a whole. Next slide, please. So for those of you who aren't super familiar with this type of work, this is a range of properties that have been measured before. We can start by looking at Letitia over here in the corner. This is a main belt asteroid. It was imaged by Rosetta, and it's got a beautiful dusty surface here and a corresponding low thermal inertia that corresponds with the thermal inertia measured on Earth of fine dust. You can contrast that with Itokawa up here. That's a near-Earth asteroid visited by the Hayabusa mission. And you notice that although it has these beautiful, nice dust pools, it also has these big solid chunks of rock. And those solid chunks of rock conduct heat very well, and that brings the overall average of thermal inertia up to about 750. And that's much higher than even coarse sand, as you see here. Next slide, please. So the model that we're working with is very capable. We're a group using 3-dimensional heat conduction. We have full self-heating and reflection. We use these advanced shape models provided by the radar team, and we need to have the appropriate computing power to deal with all of those facets that we get from them. We have variable surface reflection properties, and the most powerful thing we have is modeling over seasonal and diurnal length scales. So we can do, for example, steps every 10 minutes over a quarter of an orbit. This becomes very important for example, EV5, which Michael just talked about, where we observed it over a series of months, but we also want to measure how the surface temperature changes on a diurnal time scale, which can be about 6 hours for the object. Next slide, please. So again, this is actually the same figure that Michael just showed, but we do have great synergy with the radar astronomy group. Their 3D shape models and spin pools are really invaluable to us, and this can, we very much have been working together as 2 different teams. Next slide, please. So I just want to talk a little bit about the specific advantages of observations with the Neowise data set. And this is one example here. This is EV5 again, temperature map, and then the modeled flux in each of the 4 WISE wavelengths. And the really interesting, unique capability about Neowise is that for objects like this that are close to the sun and have all 4 bands thermally dominated, you have bands sensitive to different surface regions. So you can see here in the shorter wavelengths that you're only sensitive to the very hottest part of the object here. And so you're really only sensitive as the object turns to the southern hemisphere. You can contrast that to the longer wavelengths, which are seeing heat from much of the surface. So we actually get some level of low spatial resolution just from how the object heats up if we know the shape. Next slide, please. It's important to remember when dealing with this type of data that thermally emitted light is proportional to t to the fourth. I'm sure you all remember that from your physics class, but t to the fourth is kind of an unusual property that leads to interesting results. So for example, again with EV5, if you have two different thermal conductivity cases, this is a very low thermal conductivity and a high case, this one is actually going to be much brighter than this one because the hottest points are much hotter. There's actually supposed to be a temperature scale here that I think fell off. But these hotter points have a higher temperature, and since you go t to the fourth, what really matters is that having an extremely high point as opposed to having more hot areas spread over a larger surface, as long as your absolute value is higher. Additionally, you can see from this slide that night and day side observations can combine to create sharply measured thermal inertia. If you look at the night side of this object, it's very cold. You have this cold ridge back here versus a much warmer ridge back here. So if we can get it from two angles, which the Neowise new observations are continually adding to, this really can constrain our values. Next slide. So this is a brief teaser. I'm going to have a paper submitted in a few weeks, and I didn't want to give it away too soon, but we do have a model that's been validated against spacecraft data. We consider this to be ground truth. It's the best possible thing we can validate our data against. And these are resolved images of main belt asteroid Steins produced by Rosetta. There's a great paper out by Leroy et al. In 2011. We have a comparison of 3D and 1D heat conduction models in our paper and several new results of near-Earth asteroids. So stay tuned. Next slide, please. And next slide. So this is my new favorite object. It's 2012 HQ 124. This is the original Neowise discovery image that was just found in April. You can probably not see the little red dots in here. It's extremely faint. It's hard to see on a high-resolution monitor. We're really getting very in-depth in this data here. If you progress to the next slide, please, you'll see this orbit. The exciting thing about this object was that we discovered it in April. And when we discovered it, it was at -72 degrees declination, so very far south, where very few telescopes are. And in fact, we were the only survey that would have been able to discover this object, because right after it flew up and passed into the northern hemisphere, it flew right into the sun. So it was really only observable in the south, and we were the only people looking there. So we were able to find it in April, and then calculations, including those by John Giorgini, showed that it would pass within 3 lunar distances of Earth on June 8th. So an extremely close approach. And it's not going to be that close again until 2307. So that was great because we were able to, alert the community and the radar data. Next slide, please. The radar team was able to take great observations, which I know Lance already talked about. And in turn, I know that Michael Bush is getting his speckle data and getting a spin pole. And so we found this object. It has radar observations, and now the radar observations are going to be fed back into the Neowise observations, so we can do this type of thermophysical modeling. It's a great little life cycle with this really neat object. Marina Brozovic says it kind of looks like a sea turtle. You can kind of imagine a little head and a little shell, but it's pretty fun. Next slide, please. So in conclusion, the rich Neowise data set will allow probes of thermal inertia across populations. We've got a paper in preparation, so please stay tuned. And we're going to study HQ 124 as soon as possible next. Next slide, please. And finally, I'd like to thank the rest of the Neowise team. You might recognize the chair right here. There's James Bauer, Sarah Sonnet, John Daly, Joe Massiero, Rachel Stevenson, Tommy Graf, and me. So thank you. Yeah, it turns out that the acrylic blocks the light entirely. This is a great infrared camera we have for educational purposes, and it's interesting to see the things that block. You can also tell, I'm sorry, Amy, that Amy's got the coldest nose in the group. Sorry. And there's like this cold nose, warm nose dichotomy where it turns out people have vastly different nose temperatures, and it's not something you really notice until you go around with an infrared camera with your friends. But or your ex-friends. Sandy? So yeah, there's actually several groups with different infrared models that use various different data sets. Josh Emery has one, Marco Delbo has one, there's many, so that's not an exclusive list. But the big one that we did compare to was Cedric Leroy, and that's that full, it's a very beautiful paper. It's really like resolved thermal data. It's beautiful. And we get good match to that. We've also compared to Tom Statler's Taco model, and get good results with that as well with very basic shapes. He doesn't do the 3D shapes.